Good evening. Welcome to the first Sacramento State STEM Scholars Lecture for fall 2011. My name is Dave Evans, and I'm chair of the Geology Department at Sac State. And I have the pleasure of introducing tonight's speaker. But before doing so, I want to acknowledge the support of the Sacramento State Office of Public Affairs and Capital Public Radio, who helped to get the word out about this and other STEM lectures. And the turnout here tonight is a testament to their effort. Tonight's speaker, Dr. Dale Russell, is an adjunct professor of paleontology in the Geology Department at Sacramento State. I had the pleasure of meeting Dale about 15 years ago when we overlapped on the faculty at North Carolina State University. In North Carolina, he had a joint appointment as a professor at the university and a senior curator at the North Carolina Museum of Natural Sciences. He was lured to North Carolina after serving for nearly 30 years as a curator of fossil vertebrates and dinosaurs at the Canadian Museum of Nature in Ottawa. I was thrilled about a year ago when he said he was moving to Sacramento after retiring from the museum in North Carolina, and I was even more thrilled when he agreed to accept an adjunct appointment in our department. Dale is the kind of scientist that every aspiring scientist wants to be. He's a creative thinker who integrates topics from disparate disciplines and helps the rest of us look at the world in new ways. And he studies dinosaurs. Dale is a California native, being originally from San Francisco. He earned an undergraduate degree from the University of Oregon, after which he came back to California and got a master's degree in paleontology from UC Berkeley. From there, he went to Columbia University, where he earned a PhD in geology and paleontology. Dr. Russell's scholarly achievements are extensive and impressive. He has authored or co-authored well over 100 scientific papers, many of which have proven to be groundbreaking. He's authored 2 widely read books, An Odyssey of Time, The Dinosaurs of North America, which was published in 1989, and more recently, Islands in the Cosmos, The Evolution of Life on Land, which was published in 2009. He is noted for being the first scientist to suggest an extraterrestrial cause for the extinction of the dinosaurs, or for the Cretaceous extinctions. He proposed the controversial Dinosaurid thought experiment, in which he speculated about the human niche that Trudon might have filled were it not for the extinction of the dinosaurs. He's led field teams on 5 continents and has named about 20 new species of dinosaurs. Within the last few years, he's become particularly interested in the Pleistocene extinctions of megafauna in North America, as well as extrapolating lessons of evolution on Earth to the rest of the galaxy. So it's with great pleasure that I introduce my friend and colleague, Dr. Dale Russell.
Thank you very much, David. I forgive you for all your exaggerations. I will take them with me tonight. Thank you very much. I'm honored to be here, and I'm honored Sharon Puricelli helped me through the ways of getting here and so forth. I'm very glad to be in California again, I must say. It's a delightful state, and there's so many things to recommend it. And so it's such a diversity of interest and such lovely climate. Do you know what it takes? When I lived in Canada with my family, of course, I'm grateful to my family for being here and putting up with me again. We have precisely 1/2 a year of winter. And to come to California, you know, where there isn't any winter at all, I'd forgotten how nice it was. But anyway, it's I have to say many things, which I want to go over with you guys tonight. This is kind of off the wall. I hope that isn't the reason why you came here. But anyway, it is interesting, and I wanted to go over some of the details here as rapidly as I can. Are you hearing me all right? Or would you rather lower my voice even more? Okay, I'll struggle along then. Unfortunately, to the extent that it exists, my own expertise lies with dinosaurs and not galaxies. My interest in astronomy was not polished by precise calculations or space-age technology, but rather by the spectacle of the night sky and the fascination with life beyond Earth. Our talisman this evening are the once and truly dinosaurs, which 2 centuries ago led us into the previously unknown of life, past life on Earth. We are about to embark on a virtual journey, I hasten to say, passing planets and beyond the visible stars towards the outback of the Milky Way galaxy. At the beginning, our objective will be unclear, but by the end, I hope, we will be postulating some characteristics of dinosaur-like creatures scattered through the galaxy. Our discussion will be separated into 2 parts. The first will focus on familiar planets of the solar system, and the latter with considerations of life beyond it. We will first consider a few simple definitions, and very simple because I'm a paleontologist. What is the Milky Way galaxy? It is a spiral structure composed largely of stars that are about 100,000 light years in example, the galaxy is, and therefore incomprehensibly large. We just can't assimilate numbers that large. The sun and planets are located at a tiny spot within a gigantic band located at the distance of 25,000 light years from the galactic center. The band contains an abundance of heavy elements required for the construction of planets and the organization of life, and is largely free of planet-destroying hazards. What is a star? It is a huge accumulation, mostly of hydrogen and helium, that is massive enough to generate nuclear fusion. Within stars are synthesized almost all of the heavier elements, including carbon, nitrogen, and oxygen, the primary building blocks of life. What is a planet? Planets are accumulations of interstellar dust containing abundances of heavy elements similar to those of our parental star. They are much smaller than stars, ranging up to 1/10 of the diameter of the sun, and are insufficiently heavy to support nuclear fusion. Planetary surfaces are thought to provide the molecular foundation of life. What is life? Life is a highly organized complex of carbon-water molecules finely programmed to capture energy and employ it to respond to their environment. Primitive cells are so small that they are totally invisible to the unassisted eye. What is a extraterrestrial dinosaur? No one has ever seen what we shall call an exodinosaur, or more succinctly, exodino. Presuming they exist, universal evolutionary processes over time would have sculptured them to resemble terrestrial dinosaurs, which are often identified by their bulk, long tails, and small brains. Finally, what is the general context of our topic? About 250 million years after the Big Bang, in which the universe originated, gas clouds of simple atoms condensed into primeval stars about 100 times more massive than our sun. These stars, in turn, generated 92 kinds of naturally occurring elements. Sorry on this. Each of which is identical in its patterns of reaction throughout the universe. As a consequence, chemistry, mineralogy, petrology, and biochemistry are also uniform throughout the cosmos. Life, whether terrestrial or extraterrestrial, is everywhere built upon the same atomic scaffold. The universe is truly universal. The sun is often regarded as a run-of-the-mill star. The characteristics do not quite do it justice. Relative to the planets, it is huge, 870,000 miles in diameter, and is even large for its class of so-called G-stars. It is also relatively free of stellar storms or large flares, contains a generous component of heavy elements to aid in the formation of rocky planets, supports a broad zone surrounding it where liquid water can exist, and has been stable long enough to permit the evolution of complex life. It is our point of departure for exodinos. As already noted, the sun is exceptional in that its orbit passes through a remarkably hazard-free region of the galaxy where it is less exposed to gravitational buffeting and titanic blasts from large exploding stars. It is thus better off than 95% of the other stars in the galaxy. It was long ago recognized that the sun and planets had condensed from the same protostellar disk, and except for the concentration of hydrogen and helium in the protosun, both sun and planets were composed of the same elements in similar abundances. As the sun ignited, the younger solar wind blew gases off the inner four planets so that their rocky surfaces were exposed. The outer four planets attracted huge quantities of hydrogen, helium, and the lighter elements instead, and swelled into gas giants. They are churned by giant storms, vertical winds, and great pressures, which are almost certainly hostile to life. The surfaces of the so-called rocky planets are moons, in contrast, stable and have been mapped photographically and by radar. To obtain an impression of the variety of rocky surfaces, it will be helpful to briefly review conditions on the inner planets and some moons and their suitability as homes for life. Mercury is the smallest and innermost of the planets. Its cratered surface generally resembles that of Earth's moon, and it too has virtually no atmosphere. The wastelands of Mercury support thermal gradients that range from minus 300 degrees Fahrenheit to plus 800 degrees Fahrenheit at its equator. Like our moon, Mercury is clearly not a congenial home for life. Venus is the second planet from the sun and is considered to be Earth's twin, but its surface is very hot. Oceans and continents may have existed during the first billion years or so of its existence. However, plate tectonics, that is to say subcrustal circulation, to the geology crowd, soon ceased. The consequences were appalling. No oceans survived in which carbon dioxide could be captured in carbonate rocks. The greenhouse gas pooled in the atmosphere as surface temperatures rose to nearly 900 degrees Fahrenheit, hotter than the melting point of lead and zinc. The coolest layer near the surface of the sun is only 8 times hotter than the surface of Venus. Atmospheric pressure is nearly 100 times that of Earth. We may expect no dinosaurs, exodinosaurs, on Venus. Mars is the nearest planet beyond Earth and has long been suspected of harboring life. A magnetosphere and plate tectonics, formerly present, have long since vanished, and crater-forming impacts have blown away most of the atmosphere. Temperatures range between minus 220 degrees Fahrenheit to plus 68 degrees and are, in general, much colder than those of Earth. Due to weak gravity, Martian topography is spectacular. The highest mountain is 3 times larger than Mount Everest, and the deepest canyon is more than 3 times deeper and 9 times longer than the Grand Canyon of Colorado. 4 billion years ago, Mars had a much denser atmosphere and probably an ocean of liquid water, but life, if it were once present, dwindled as the ocean evaporated. Landscapes of Mars forcibly bring to mind the wreckage of an Earth-like planet. It is a place where time ran out. Europa, a moon of Jupiter, is almost as large as Earth's moon, and bears a thin atmosphere of oxygen, but was not generated by living organisms, the oxygen. This is Europa, a moon, not a planet. Surface radiation levels would make humans ill. Europa's surface is smooth and laced with movable cracks, the largest of which are over 10 miles wide. The outer crust is solid ice, about 10 miles thick, beneath which is a liquid ocean 60 miles in depth, and slightly more than twice the volume of Earth's oceans. The subsurface ocean seldom, if ever, interacts with the surface, although it is in direct contact with silicate rocks below. Its liquid condition is believed to be sustained by tidal heat from the gravitational pull of Jupiter. One hemisphere is always turned towards its giant neighbor, as is the famous case of Earth's moon. Microbial life could barely, if at all, be present in hydrothermal vents similar to those of the floor of Earth's oceans. Titan, a moon of Saturn, is larger than the planet Mercury. Surface light is dimmed by smog-like screen of carbon molecules, and surface temperatures are colder, about 290 degrees Fahrenheit, than those of Mars. As with Earth, the atmosphere is mostly composed of nitrogen. Atmospheric pressures are 1.5 times those of Earth, so that water life on its surface neither evaporates nor sublimates, but instead forms what is termed rock ice. Surface gravity is so weak and the atmosphere so dense that with paddles attached to our arms we could fly. Titan's surface floats on an ammonia water ocean. Lavas of mixed water, methane, and carbon dioxide erupt from volcanoes, and rivers of liquid methane erode rock ice and feed drainage patterns that amazingly resemble water drainage on Earth. Oh my, I see, things are happening. Okay. Clear lakes of methane form from the poles during winter, while in equatorial regions, eroded grains of rock ice stained with sulfate are blown into vast dune fields. It would seem that only molecular precursors of life could be present on Titan. Considering its peculiarities, Titan can best be condensed as an odd cartoon of a life-bearing planet. Now, to go through some of these, this, of course, is our Milky Way galaxy taken from mountains in New Mexico. This is the Milky Way gravity, and you can see the sun in the lower part, so it's off-center from the galactic center. This is the solar system of the sun and its planets, and you can see they're relatively drawn all to the same scale. You can see that Ceres and Pluto are approximately the same size if you can see them at all. And this is the reason why Pluto, of course, fell from the list of planets a short time ago. This is an average run-of-the-mill but rather beautiful duck-billed dinosaur, and this may be considered as more or less representing a highly evolved dinosaur near the end of the Cretaceous period. This is a beautiful, how can I say, extraction of a dinosaurian embryo. This is to represent actually life in our presentation tonight. You can see very carefully, I should have brought a pointer up, but oh, am I connected? Good. Right here is the orbit of the eye, and here are the nostrils. The body is kind of curved around here, and it's been eaten, consumed just after it died by little beetles, so that they've taken the bones apart, and they're disarticulated, unfortunately, but it's rare that we get dinosaur embryos in general, and this is a beautiful example of what is best about this fossil record. This is, of course, Mercury, and that is the surface of Mercury, which looks like that of the moon. It contains a lot more iron in it than the moon does. This is Venus. One of them is the one of them is the cloud-covered surface of Venus, as you're probably familiar with, or you know about, I'm sure. And the other one is seen through radar, so that the topography of Venus can be seen. This is a Soviet Russian lander that landed on the surface of Venus, along with several others, approximately 30 years ago. And these are the only projectiles that have existed or reached the surface of Venus, and most of them ceased functioning after about an hour or an hour and a half because of the intense heat on the surface of Saturn. The color is not true. It absorbs the atmosphere of Venus absorbs practically everything in the higher vibrations of color. This is a lovely picture of where we are. If you look closely, the blue planet is registered very well. You can see the Great Valley of California and fog blowing off of the Pacific Ocean. And you can probably identify your own homes there somewhere. This is a lovely example of what isn't barren. This, of course, is taken in Ecuador. This is Mars, taken by the Hubble telescope. This is the surface of Jupiter, not Jupiter, heavens. Come on, guys. I'm having a Mars, for heaven's sakes. Yes, and Mars is such a beautiful photogenic planet. I just love it. And there's so much known about the geography of Mars. It's truly magnificent. On the right is a picture that I took in the southwestern part of Egypt, which is the hottest and most desert place of the Sahara Desert. And then on the opposite side toward me is the crater on the surface of Mars. So you can see on extreme environments on Earth that you grade into sorts of situations, environments that are similar. This is the moon of Europa with the ice, so-called, I believe it is ice. People know more about this than I do. But it certainly does not look like the North Pole from the high elevation and it has what seems to be a lot of iron in it because it marks the trajectory of these cracks. And this is an example of freezing and thawing, I suppose. And this is a lovely picture of the moons of Saturn, and one of the Titan is the big blurry ball in the background. And this is the only picture of Titan that I know of that has been taken by a lander that could take pictures on the surface of it. Okay, we'll stop there. I'm going to back up one and leave it there for the time being. The litany is clear and disappointing. Out of 7 planets and 2 large moons, none exhibit surfaces known to sustain life, and all are uniformly barren. Only one planetary object in our solar system is known to harbor life, yet the distribution of life on this planet, our Earth, is far from uniform. Some regions teem with life, while in others it is space, and in still others it is absent altogether. The Earth thus richly exhibits space-time phenomena that inform us of the evolution of life on our planet, and probably also on any planet in the solar system, beyond the solar system. We must, I think, use the Earth as a key to the understanding of exobiology. Natural selection is generally considered to be the engine of evolution. It is widely understood that survival of the fittest produces adaptation to challenges in the environment. Typically, physical factors do not react to the presence of organisms. To survive, organisms must adapt. The long-time physical attributes of Earth's surface have been abundant water and mild temperature, both recognized as necessary for life. We have noted that there are no oceans on Mercury, Venus, and Mars, and surface temperatures on Europa and Titan are frigid. All are far from ideal homes for life. Natural selection also generates biological as well as physical challenges. Examples include digestion and reproduction, which together support biodiversity. The difference between physical and biological challenges is that organisms respond to other organisms which typically react to them in return, hence the term struggle in the struggle for existence. Organisms walk on rocks but struggle with other organisms. Thus, the engine of natural selection has 2 modes. The diversity of life has increased by more than 1 billion times since it first appeared on our planet. Single-celled organisms have given rise to organisms containing trillions of collaborating cells, reflecting increasing body size. The accomplishments of bacteria are impressive, but so is the ability of the human brain to process 1 billion synaptic operations per second. In mammals and birds, average brain-to-body ratios reflecting relative brain size have increased by a factor of 20 over the past 100 million years. As evidenced by skeletal structures and fossil trackways, average animal activity levels reflecting the pace of competitive interaction have also increased. Together, these trends reflect a major expansion of the biosphere. It is obvious that this has happened. However, the physical environment remained essentially unchanged. How did this huge expansion come to be in the absence of huge supporting trends in the physical environment? What was happening? Let us examine the pace of biotic change through time more closely. Bacteria slowly multiplied in diversity during the first 3 quarters of Earth history, when only single-celled organisms were present on our planet. During the last quarter of Earth history, multicellular organisms appeared, diversified, and rapidly expanded their neurological behavioral repertoires. Rates of evolutionary change not only increased, they accelerated. This was evidently a result of competition between organisms, which by its nature is self-stimulating. Over a very long interval of time, biotic selection has increasingly outpaced physical selection on Earth. If acceleration is an evolutionary norm on Earth, it is difficult to understand why it would not apply to biological systems elsewhere. Yet it is obvious that the Earth does not everywhere possess ideal blue planet conditions that support rapidly evolving ecosystems. After nearly 4 billion years, the biosphere occupies only 0.2% of the volume of our planet, and 88% of liquid water in the crust still remains devoid of life. The oceans, extending over twice as much of the Earth's surface as land, support only half of the planet's living tissue or biomass and contain only one-tenth as much of the planet's species or biodiversity. Species diversity is impoverished in frigid or arid environments prevailing across 60% of the continents. Warm, moist, and stable physical environments where life is most diversified cover only 30% of continental surfaces. An inverse relationship between biodiversity and physical stress indicates that life tolerates extreme conditions poorly. And although they may be widely dispersed, fertile lands are a very important segment of life on Earth. The effects of physical stress are obvious. If we imagine a map of the world, we usually scan it from a west-east direction, for example, from Sacramento to New York or Paris to Tokyo, following the temperate zone around the planet. Temperatures do not change greatly, and we gain an impression of living on a generally green planet. However, our perception of the planet is vastly different if we travel from warm rainforests of Brazil to temperate forests of the Olympic Peninsula and on to the cold spruce forests of the Yukon and finally to the barren tundra of polar Canada. At last stop, we would feel the frigid and arid landscapes of Mars must not be too far off. Conversely, if we reverse direction, our journey will begin with primitive mosses on Earth on the far north, proceed south through seasonally wet conifer forests reminiscent of the Coal Age, through broadleaf forests recalling vegetation late in dinosaurian times, and ending in the raucous biodiversity of modern equatorial jungles. In this case, progression appears to imitate the evolution of life through time, from simple to more complex biological systems. Time can thus be regarded as a positive physical attribute, whereby more time is better. How then do dinosaurs fit into the progression of life on Earth? 75 million years ago, the Earth was warmer than it is now. The poles were free of ice, and hot deserts rather than jungles girded the equator. Dinosaurs inhabited both polar and equatorial regions, but the record they left behind is most complete in lands bordering the Rocky Mountains of the US and Canada. Imagine low plains resembling wetlands of the Sacramento Delta, with banks lined with palms and odd broadleaf trees and watercourses inhabited by familiar-looking fish, catfish, turtles, lizards, alligators, and small mammals. Here and there are irregular lines of browsing herbivorous dinosaurs only slightly larger than modern big-game animals in Africa. Shapes are oddly familiar. There are horse-like duck-billed dinosaurs, rhino-like horned dinosaurs, dinosaurs resembling giant armadillos, ostrich-like dinosaurs, several varieties of dinosaurian baboons with supple hands, and medium-sized tyrannosaurs resembling large carnivorous ground birds. They all match their names recognizably well. The plant eaters handle vegetation roughly, tearing off reeds and branches wholesale and pushing over small trees to consume the crowds. Carnivory is much more revolting, for the flesh eaters prefer immature herbivores, crushing bodies and bolting them down in chunks. Pursuits are rapid but linear, for neither predator nor prey can dodge well. These are extensive seasonally occupied nesting grounds, probably at some distance from the rivers because they flood, and you're well acquainted with that. Hatchling dinosaurs are also snatched by huge intercontinental flying reptiles that cross the equator to attend seasonal hatchings in both hemispheres. In general, overall impressions call to mind a barnyard wherein strangeness marks scenes that are simultaneously mundane and unfamiliar. Is it not rather extraterrestrial? We have noted that these dinosaurs lived 75 million years ago, and our panorama is representative of the acme of the Dinosaurian era. What had been achieved during the preceding 75 million years? It appeared that dinosaurian diversity had increased, activity levels had also increased, average brain-to-body proportions doubled. The later dinosaurs would have outcompeted their more ancient predecessors. Conversely, how would these 75 million-year-old dinosaurs fared against their modern African counterparts? Succinctly, they would have been thoroughly outclassed. Skeletal architecture is much more finely tuned among modern big game, and it's beautiful to go into a place where you can see skeletalized mammals and compare them with pictures of dinosaur skeletons themselves. It's really startling. The skeletal architecture is much more finely tuned among modern big game, indicating they have much greater ability to dodge. Carnivores tend to pursue their prey now rather than pounce on it. Modern herbivores live longer, have fewer and heavier offsprings, and parental care is much more effective. As noted before, average brain-body proportions have increased about 20 times, implying hugely more complex behavioral options. In general appearance, large animals probably looked more youthful, not older, and behave in a more energetic manner than did their dinosaur predecessors. Looking back, the Dinosaurian era endured for over 150 million years, beginning with records from 220 million years ago and ending with their extinction 65 million years ago. It spanned a geometric midpoint in the history of life on Earth. The evolution of large animals appears to be congruent with accelerating competitive fitness. It seems reasonable to suppose that life on other planets in the galaxy would also show equally dramatical patterns of biological improvement. This is a rough idea of the diversity increase on a species level through geologic time, and it's elapsing rather than in millions of years before present. It's elapsing time, and the age of dinosaurs falls approximately in the geometric middle. This is a NASA picture showing where plant vegetation is most copious, and this shows approximately, you can see the Sahara Desert there, and the Arabian Peninsula very well, going on off into the western parts of China and also Australia. They look kind of pale green to me on the map, but I can assure you they are not that color when you're living and walking among them. So this gives you also an impression on the ice fields of the south of the distribution of non-ideal environments throughout the land of our own planet. This is a picture in Zambia of an elephant, or a heffalump as we like to call them, compared to a high latitude musk oxen up there. We had some Chinese folks with us who were taking pictures leaning over their cameras, and I was afraid that the musk oxen would charge, because a musk oxen went up and down like this, and our Chinese colleague did this, and it looked like it was going to have a very unhappy ending and an international catastrophe. Now this is rather, these are actually a kind of horned dinosaurs you probably recognize outside the Tyrrell Museum in Alberta, and they demonstrate the size of a rather typical animals, dinosaurs of latest Cretaceous age. Look at the tail size, look at the ornamentation on the head, general size. They're little, about twice as high as I am on the rump, going over the top. Looks like I got a little too exuberant here. Russell's law is nothing as easy as it looks. And there it is. Good. It must be stressed that galactic environments do pose threats to the survival of life. Dinosaurs have long been considered as victims of catastrophe. For many years, their demise was attributed to climatic change in the form of globally cooling climates and or the withdrawal of oceans from continental margins. A turning point came when scientists at UC Berkeley found evidence of an impact that an asteroid 6 miles in diameter coincided with a biologic catastrophe. The simultaneous extinction of dinosaurs was one of the 3 greatest biologic catastrophes to have occurred during the last 500 million years. To the last, dinosaurs were distributed from pole to pole and around the world, often in great herds. Their anatomy was flexible enough for some dinosaurs to give rise to birds. Many more bore more offspring per year than rabbits do. Had the asteroid not struck, their descendants would, in all likelihood, still dominate terrestrial biosystems. That they became extinct in a catastrophe is more a tribute of the power of the impact than to the intrinsic weakness of dinosaurs. A different biologic disaster of solar system proportions took place in Antarctica. During the latter part of the Dinosaurian era, lowland climates were cool with light winter frost. Antarctic dinosaurs were present up to the time of their general extinction, but by 35 million years ago, temperatures had cooled and glaciers began to spread into Antarctic lowlands. The coldest temperature recently recorded in Antarctica is minus 128 degrees Fahrenheit. The largest animals now living in its interior are 2 species of midges, the more imposing of which is half an inch long. A lake was recently discovered, perhaps you've heard about it, in central Antarctica that is 160 miles long and 30 miles wide. However, it lies in utter darkness, separated from the surface by nearly 2 miles of glacial ice. Whether or not it supports microbial life is unknown. The lake and its surroundings are reminiscent of the moon Europa, with its subterranean ocean capped by a thick layer of ice above and in contact with silicate rocks below. Antarctica lies well outside the so-called habitable zone of the solar system. Antarctica's misfortune was limited to part of a planet. Other hazards have the capacity to impair or eliminate entire planets. The growth of planets from the Protoplanetary Nebula includes 2 phases. First is a gravitational assembly of nebular dust and gases into Mars-sized planetoids. The second is violent, as planetoids are swept together in giant impacts to form planets. Massive primeval impact events shattered both primitive Mercury and primitive Earth. Proto-Mercury lost its primary atmosphere almost entirely. Proto-Earth lost much of its atmosphere but gained the Moon as a stabilizing companion. Proto-Venus lost significantly less of its primary atmosphere, and as a consequence, its surface was transformed into a furnace. Conversely, Proto-Earth, relieved much of its greenhouse gas burden, was transformed into a benign home for life. Fortunately for the dinosaurs and for us, what might have seemed a horrendous catastrophe was instead a very fortunate accident. As the planets arranged themselves into more or less stable orbits, they were pummeled by a rain of solar system debris driven by gravitational slingshot events. The results are still visible on the cratered surfaces of Mercury, Mars, and the satellites of the outer planets. A crater over 100 miles across and buried in the subsurface of Yucatan in Mexico was made by the asteroid responsible for the extinction of the dinosaurs. Beyond the solar system, the powerful gravitation of giant planets have evidently catapulted neighboring planets into interstellar space. There they orbit the center of the galaxy, twice as abundant as stars, but emitting no light, and encounter with the Jupiter-sized rogue planet would easily destabilize the planetary system. Another hazard for planets is the violent explosion of giant stars. Termed supernovae, they consume their hydrogen-helium fuel at very high rates and implode in a gigantic burst of energy. For several weeks, they shine nearly as brightly as the other stars in the galaxy combined at a distance of 10 light years away. They would shine as brilliantly as the sun shines upon us at midday at a distance of 10 light years. But the sun is only 8 light seconds away, not 10 light years away. Even 100 light years away, the burst would remove the ozone layer and expose Earth's surface to a lethal solar and cosmic radiation. These gigantic explosions have not yet been firmly linked to any of the several catastrophic extinctions on Earth. The life of an individual organism may at times be precarious, but the evolution of life has generally been a steady and positive process. Living organisms have precisely regulated the many greenhouse gases, including carbon dioxide, water vapor, methane, nitrous oxide, and ozone, so that the Earth's surface has been favorable for life over 3 billion years. Just enough carbon dioxide remains in the atmosphere to support abundant photosynthesis, and levels of oxygen have risen to support highly active animals. Nitrogen provides a sort of vaporous roughage to keep partial pressure of vital gases high. Without life, Average temperatures on Earth would be below 0 Fahrenheit and below habitable conditions as defined by exobiologists. The entire planet would resemble Antarctica, but the balance of the gases will not last forever. By another 100 million years, the oceans will have evaporated and the Earth will come to resemble the present Venus. This is the Chicxulub impact crater in northern Yucatan, where the this was the site of the impact of, we don't know where it came from. It was thought for a while that it was from the asteroid belt, but I don't know. Anyway, it came through the atmosphere with the speed of a bullet and considerably more. This is Antarctica, a beautiful reconstruction of the Antarctic continent. There's lots of very interesting record of life before, up to the time of 35 million years ago. But now it is practically dead. It's the greatest catastrophe that has ever happened on Earth that we know of. This is a impact of a planet and a planetoid, or it could be a rogue giant with another planet. And this, on the lower left-hand corner, is an exploding star. And you can compare its luminosity with the center of the galaxy, galaxy that it belongs to, way in the outer reaches of it. Okay, a recapitulation. Let us recapitulate. By examining the solar system with telescopes and rocket-propelled probes and picks and shovels, we may postulate many things, among which are the solar system benefited from the sun's fortunate location in the galaxy. A collision can destroy planets in minutes, but it also can produce positive results that endure for billions of years. Interplanetary dust possesses remarkable potentialities, among which is a capacity to form life. The presence of life is not to be confused with the lifespan of a planet, nor is life present just because a planet bears abundant water. Life is neither abundant or even present everywhere on Earth. There is structure in the evolution of life. Evolution is not fundamentally random. The record of life on Earth strongly suggests that biologic fitness accelerated in the past and is likely to continue to do so for some time. The Dinosaurian Era marks a geometric midpoint in the evolution of life on Earth. An examination of life on Earth reveals much about the limitations and possibilities of extraterrestrial life. It will be significant if life is found on Mars, Europa, and/or Titan, and the opposite is also true, and certainly many things remain to be discovered. Our solar system contains 5 basic varieties of planetary bodies, only one of which harbors life. Rocky planetoids with sparse, if any, reservoirs of water, such as Venus. Rocky planetoids with large reservoirs of water that may or may not host life, such as Earth. Water planetoids lacking continents, such as the moon Europa. Cold gas giants, such as Jupiter, and ice giants, like Uranus. We will now proceed to the newly appreciated outback of our galaxy. The 5 planetary varieties of the solar system, the 5 planetary varieties, at least 4 are new. Now, recently identified, none appear to be equal or to surpass the Earth as a home for life. These include planets made largely of carbon instead of silicates, planets made largely of iron, similar to planetary cores, super-Earths more massive than Earth and less so than gas giants, and often covered with a hot universal ocean, and hot Jupiters near their central stars. To return to the exodinos, what would they look like? Again, the experience of Earth might provide insights. If nothing else, natural selection has been pragmatic. It would therefore tend to select a limited number of body forms that would most effectively promote competitive success. This process is not random. Stellar radiation may not be the only source of biological energy, but it probably provides the greatest and most accessible source of energy in most stellar systems. Photosynthetic processes on planets would be selected to tap energy-rich stellar radiation. Thus, planets of blue stars would bear plants with red leaves. The leaves would photosynthesize with blue and reject the red. In the case of less brilliant stars, plants would absorb a wider spectrum and thus bear dark or black leaves. Green leaves would, of course, identify radiation from an intermediate star like our sun. Exodinosaurs would tend to be camouflaged to match the color of the vegetation in their environments. Red versus black hues would thus characterize exodinos of the two extremes. Dim stars are more abundant than brilliant stars, so black exodinos would be more common than red ones. The skeletal structure of an exodino would also reflect the strength of gravity on the planet. Thus, large planets would tend to host small hippo-like exodinos, and small planets would tend to host large gazelle-like exodinos. Of course, metabolic needs would also be affected by gravity. Suffice it to say that a heavy Exodinosaurus rex would need lots of exoburgers. Pragmatically speaking, plants are usually structured to intercept light with leaves and be fixed to the ground by stems or trunks. Animal consumers are usually ambulatory. These generalities would probably apply to most land-based exobiological systems and would constitute the body form of larger organisms. Trees and four-legged animals would be the rule, but variation on themes would also be common. For example, during the latter part of the Dinosaurian era, continental drift and spreading equatorial oceans had separated dinosaur-dominated biosystems on northern and southern continents for 100 million years. Dinosaurs in both hemispheres were recognizably dinosaurian, but their bones no longer resembled each other in detail. Interplanetary space certainly cannot be crossed by exodinos, and exodinos from different planets would thus be distinguishable as well. Following the extinction of dinosaurs on Earth, several groups of mammals became larger and reoccupied niches formerly filled by dinosaurs. Natural selection simultaneously altered body forms of large terrestrial animals toward larger brains, simultaneously altered body forms of large terrestrial mammals towards larger brains, more efficient dentitions, more gracile bodies, and shorter tails. Through time, the same processes would have altered the body forms of exodinos in the same directions. The appearance of exodinos would thus impress interplanetary voyagers as being interesting and often marvelous, but not astounding or freakish. Back on Earth, if we wish to ponder dinosaurian biosystems, there are at least two options. One is to visit places supporting living fossils that resemble organisms in existence when the dinosaurs were alive. This is a good option and one that should be considered more often. Acid soils are stressful for many organisms, and those inhabiting islands are in danger of being exterminated by invasive organisms. Interestingly, very close to us in Sacramento are acidic redwood forests, which recall forests of the real Jurassic Park. The bald cypress swamps of the American Southeast are hauntingly reminiscent of environments in southern Alberta just before the dinosaurs became extinct. And perhaps the most cogent of all are the precariously surviving forests of New Zealand and New Caledonia in the southwestern Pacific. They are best appreciated in the moonlight when the feeling of the Dinosaurian era is almost popular. A second and more traditional option is, of course, to search for terrestrial exodino bones in rocks deposited between 220 and 65 million years ago. There are few things more thought-provoking than brushing away ancient sediments to reveal the remains of a large animal that last saw the light of day 75 million years ago. Unfortunately, the sense of wonder would not have been reciprocated. The creature would have been unable to understand that its excavator was a brainy organism whose genetic information had been transmitted on fragile molecular threads from the Dinosaurian era to the present. There are evidently lots of living exodinosaurs. A recent telescopic space probe estimates that 30,000 planets bearing liquid water are within 1,000 light years of Earth. Considering the record of life on Earth and the population of stars in the galaxy, there could be as many as 80 million water-bearing planets in our galaxy. To find a particular exodino-bearing planet, we would have to find one that corresponds in age to the Dinosaurian era on Earth, which lasted about 150 million years. Sadly, there is no way modern astronomy can identify increments of time as precise as that. for the age of a particular star with a suitable planet can now only be estimated to within 1 billion years. It may take some time before we will be able to spot exodinosaurs by the age of their planets. And I'd like to show you a final bunch of slides. This is a formation which could be considered an exodinosaur, and I think it's rather, it could be. There are animals on Earth, for example, like glyptodonts, giant armadillos, of course, dinosaurs that lived in the later part of the Dinosaurian Era, and pangolins and other sorts of creatures. So this one, to me, is an acceptable Denisopaleo dinosaur. This one, I think, is a lovely example of what is shocking, and it really is indigestible. This looks like an animal that probably wouldn't survive very long in East Africa today. It's rather pathetic, really, and you know, it's something that I think was put together by different body parts just for fun to see something that would be extravagant. Now, these are landscapes of, from a violet high-frequency emitting star, and shows the plants, of course, are emitting the red light, which they're not consuming. And this is a situation where the stars are dim, and the plants are, if they are there, they're doing their best to get as much light as they can. This shows I think this is kind of fun. This one is from approximately 140 million years ago, and you can see that the northern and southern continents are separated and continue to be so. And believe me, it is very easy, for the most part, to distinguish dinosaur bones from the two hemispheres. And of course, this would be an example of parallel evolution, which would approximate chatter or peculiarities in the environments that they are inhabiting. On the left is a picture that I took on the mountain of Mount Doe in New Caledonia, which was absolutely lovely, and I really felt that I was in the Jurassic at that. There were practically no birds. It was quiet. The vegetation was very archaic, and they had large bats that flew around resembling pterosaurs. Oh, the other one is from New Zealand, actually. It's this is a Gathus, kind of an Araucarian tree, which is now restricted to the southern hemisphere, and this is one of the biggest trees in New Zealand surviving today. And this gives you an idea of a gigantic upside-down asparagus. Now, these are animals living today that I think would have the flexibility of a dinosaur or something in the Dinosaurian era. The one on the left is a Komodo dragon. The one on the right is an emu. And I really am impressed with the emu, because when you look into the eyes of that creature, I think you're looking virtually into the eyes of an ostrich dinosaur. And that shows you something of the mentality. The brain size is about the same. The adaptation is the same. And a lot of these running cursorial dinosaurs had feathers, as we know now. And this is the last slide, and it's a sunset on Mars. Mars, of course, is about twice as far away from the sun as the Earth is. And Mars is a beautiful planet, even though it's probably very close to being dead. The apparent fact that tens of millions of planets are presently harboring exodino-dominated biosystems in the Milky Way galaxy is alone breathtaking. At this moment, however, prudence overtakes conjecture, and we must be content to know that in all probability there are many kinds of dinosaur-like creatures inhabiting many Earth-like planets scattered through the more tranquil regions of the galaxy. More thought will be required to nourish our innate desire to know. It's really not only curiosity, it is a search for the meaning of life. And there are so many interesting unknown avenues to explore. After all, Mars may have come very close to being a home for life. Thank you very much.
I think we have about 5 minutes for questions, if there's any questions.
Do you have any idea of the approximate lifespan
Yes, well, I don't, but my colleagues do, fortunately. And they vary in general age. The way the high reproductive rates suggest low, short lifespan. So that some of the common duck-billed dinosaurs, for example, it looks like they probably didn't, on the average, live longer than, say, 10 or 15 years. So we're not looking for great longevity. On the balance, some of the sauropods are really Brontosaur-like. They had 30 or 40 years. And so there must have been horrific predation on young baby dinosaurs. And probably when the adults reached. Now I know that, for example, you can sometimes change. Oh, I'm so sorry. This is not a microphone. Oh, it is. Okay. Oh my gosh. Okay. Because you can tell there's kind of a time when you grow fast, and the same thing occurs in dinosaurs, and it's like rings of a tree. So when the rings get very tight, that means a dinosaur, if it's a lady dinosaur, is reproducing. And so then the rate of increase is smaller. And very few of these animals have been examined a lot, but it would look like probably the oldest dinosaurs that we know would be maximum 60 years. And I think that would be, see, dinosaurs didn't necessarily live a long time. That's what we have to understand. And I think that turtles do a much better job. I think there are turtles on other planets too, incidentally. Yes, sir? No, they're different. They're in two different family groups, and they're quite a lot different. It's not too difficult to tell them apart. They're quite different, actually. As you probably know, a brontosaur in general is built on a kind of like an elephantine-like adaptation. But unlike an elephant, the head is small. There's not much brains in them, so they put the head at the end of the neck. But an elephant who has a heavy head and a lot of grinders and molars and such in its mouth solved the problem by pushing his head back onto the body, and the trunk comes out where the dinosaur had a head. So it was more efficient for some animals. They have to follow their... they have long things to eat with, is the message there.
Well, there's no other questions. I'd like to thank you again.
Thank you very much.